Okay, thank you. So now we're going to introduce David Chen from University of Rochester. Field was in physics. His advisor was Rip Collins, I think a familiar name to a lot of us at the laboratories. Practicum was done in 2021 at Sandia National Laboratory, and the title of the talk is Electronic Structure of Iron 2, Oxygen 3 above 700 gigapascals. So David, the floor is yours.
Thank you. So hi everyone, my name is David, or I actually go by my middle name, which is Alex Chin. So I'm from the University of Rochester, and today I'm going to be talking about some of the work we've done characterizing the electronic structure of Fe2O3, or hematite, above 700 GPa. So on my title slide, I'm showing some absorption spectra of Fe2O3 here on the left, and I'm showing a few of the different pressures that we were able to reach at the Laboratory for Laser Energetics. And I'm really highlighting this Preedge feature here. And this feature is sensitive to how the neighboring oxygen atoms perturb the iron 3D states. I'll begin with a summary for my talk. A new X-ray spectrometer was used to measure the behavior of iron valence electrons at planetary core conditions. Xaxis is capable of characterizing both the crystal and electronic structure of matter at high energy density, or HED, conditions. We measured Xapp's data of compressed Fe2O3 above 700 GPa, and analysis shows that the oxygen ion potentials become skewed and the iron D states broaden with increasing density. And these results indicate the persistence of iron-oxygen bonding above 400 GPa. I'd really like to thank my collaborators for this work. There's a large group from the University of Rochester, Princeton University, Sorbonne University in Paris, France, and Lawrence Livermore National Lab, along with the SSGF, of course. So I'll begin with some motivation and context for this work. Few experiments are capable of understanding chemical bonding and electron structure at high energy density conditions. And just briefly, what do I mean when I say HED? It's loosely defined as pressures above 100 GPa or above 1 megabar, and this is equivalent to 10 to the 11 pascals. And just for context here, atmospheric pressure is around 10 to the 5 pascals. So we're really compressing these materials to extreme conditions where new phenomena starts to occur. And for context, I'm plotting a phase diagram here. We have temperature as a function of pressure, and I have a few different objects to put into context here. We have our rocky planet cores on the bottom left, then we have our gas giants, and then we go up in temperature and pressure. We can get to solar cores and ICF, what we heard about yesterday. My work primarily focuses on rocky planets down here. At these conditions, there's really few techniques that can characterize electronic structure. So some of them include reflectivity measurements, which show insulator to metal transitions and these new electride phases. But these measurements are really surface measurements and require the material to be reflective, so they're semi-limited. On the other hand, X-ray scattering and Raman measurements can diagnose electron structure, but these really require large photon fluxes, which are difficult to achieve at a lot of the large laser facilities. So XApps, or X-ray absorption fine structure spectroscopy, is a technique that's capable of characterizing electron bonding and electron structure at planetary core conditions. So the material we chose to study is Fe2O3. So why do we look at Fe2O3? Iron oxides under extreme environments influence the evolution of the Earth and super-Earths. So here I'm showing a cutout of the different layers of the Earth. We start at the crust, and then we work down into the mantle, which reaches conditions of a few hundred, 125 GPa, and then all the way down to the core of the Earth, where we reach 350 GPa. And at the Laboratory for Laser Energetics, we can access all of these different conditions and compress Fe2O3 to these extreme conditions. And some of the interesting things about Fe2O3 is that many different stoichiometries have been identified in iron-oxygen systems up to 120 GPa, and different oxidation states have been identified as you compress iron oxides. So what we really wanted to answer is what happens to Fe2O3 when we compress it down to these core Earth conditions. So what is the current status of Fe2O3? The crystal structure has been mapped out up to 400 GPa. Fe2O3 begins in the alpha, or hematite phase. This is iron surrounded by 6 oxygen atoms in an octahedral structure, and then those cages are stacked together. It's found to undergo a series of phase transitions up to around 120 GPa, and then the theta phase was found to be stable. This is iron surrounded by 6 oxygens in a trigonal prism structure. And one of the really interesting things that was found, and this was done by Ian Ocampo at Princeton, who's a collaborator, they found that they lose diffraction lines when they compress it above 400 GPa. And what this means is Fe2O3 appears to lose long-range order. There's no long-range crystal structure in Fe2O3. And so there's really an open question about what is happening to Fe2O3 at these conditions that we can answer with X-ray absorption fine structure spectroscopy. So that's to motivate this work. Now I'll briefly talk about what is XApp, this acronym that I keep throwing around a lot. The X-ray absorption spectrum is produced by interactions of the X-ray with the core electrons and exciting those core electrons into the continuum. So here, I'm showing the absorption spectrum of Fe2O3 as a function of energy. And I've highlighted two regions, the X-ray absorption near-edge spectroscopy region, or the Zanes region, and the extended XApps region, shown in blue here. What you want to think is happening is we have an X-ray coming in, it's knocking out a core electron, and that core electron gets excited. If that core electron is excited to a bound state just below the continuum, you can get pre-edge features, little features in your absorption spectrum before the main spike. When the X-rays have enough energy to excite into the continuum, you see this large spike in absorption. And then if that X-ray has enough energy to excite it into the continuum, that electron will scatter off of neighboring atoms. And that scattering actually impacts the probability of the X-ray being absorbed in the first place. And so that's what produces modulations in the extended region. So just to reiterate, the Zanes region is sensitive to electron transitions just around the continuum. So it's sensitive to the electron density of states just around the continuum. On the other hand, the extended XApps region is looking at exciting that electron out, scattering off of neighboring atoms. So it's sensitive to the local structure of the neighboring atoms around the absorbing atom. So just to talk about Zanes a little bit more, Zanes is sensitive to the electron structure around the continuum. So here I have a little cartoon of the density of states as a function of energy, and I'm highlighting my K, L, and M shells, or my N equals 1, N equals 2, N equals 3 shells. And we're looking at transitions from the K shell into the continuum. And we can only transition into unoccupied states, and the occupation of the density of states is controlled by the Fermi-Dirac distribution. So here I'm showing a really simple absorption spectrum that you would get from transitioning from this K shell into the unoccupied states. So, for example, if we were to heat the material, the slope of the Fermi-Dirac distribution would change, and this would cause a change in the slope in our Zanes spectrum. On the other hand, if we increase the density, we can cause shifts in the energy levels, ultimately causing shifts in our absorption spectrum. But this is really a simplified picture, and the electron density of states is very complex around here. So other factors must be included when we look at real spectrums that I'll show later on. Now to talk about the extended XApps region. The extended XApps modulations are produced by scattering of the photoelectron off of neighboring atoms. So here I'm showing an iron absorption spectrum as a function of energy, and I'm highlighting these extended XApps modulations. And just as a note here, we often call these modulations chi, where chi is just the isolated modulations on this absorption edge. And the image you want to have in your mind is we have an X-ray coming in. It's going to knock out a core electron. That core electron's wave function is going to expand radially outwards, reflect off of neighboring atoms, and the reflected and outgoing wave functions can interfere constructively or destructively. If they interfere constructively, you get peaks in your absorption spectrum. And if they interfere destructively, you get valleys. And so this interference pattern is a function of how much energy you give to the electron, and therefore you get these different modulations on your XApp spectrum. The XApps modulations depend upon the radial distribution of atoms surrounding the absorbing atom. So for each given, we have an absorbing atom where we're scattering off of a neighboring atom. The XApp signal that we would get, the chi modulations, we would get for one scattering atom, and then we would sum up all possible paths. So the XApp signal for one scattering atom is given by this equation here, and it's an integral over what I'm calling the real distribution, where the real distribution is the probability distribution of the scattering atom relative to the absorbing atom. So if this material was fixed and frozen in place and there were no defects, this would be a delta function. But as we heat up, this distribution gets wider. And then as we reach really extreme conditions, interesting things can start happening to this distribution, where it can start becoming skewed or asymmetric. Okay, so now that we have a very basic understanding of what XApp spectroscopy is, I want to briefly talk about how we do these experiments. So we do all of these experiments on the Omega 60 laser facility at the Laboratory for Laser Energetics at Rochester. It's the same facility that Patrick did a lot of his work on. Samples were probed Samples were compressed to core Earth conditions, or around 5 nanoseconds, and probed with a broadband X-ray source for around 100 picoseconds. So these experiments start with a sample, and we sandwich it between 2 diamond pieces, and then we compress it with a laser for around 5 nanoseconds, and we reach conditions between 100 and up to 700 GPa. Once we get to those conditions, we try to hold the sample there. We use VISAR, or a velocity interferometry system, for any reflector. Basically, this is just a laser that we send off of a silicon mirror off the back surface of the diamond. And we use that to measure the velocity of the back surface of the diamond. And then we take that velocity and we back propagate it to determine the pressure in the sample. Once our sample reaches the extreme conditions, we fire our implosion backlighter. This is a plastic shell that we illuminate with around 20 kilojoules of energy. We cause that plastic shell to implode, stagnate, and it emits a bright X-ray flash when it stagnates for a very short amount of time. Those X-rays pass through our sample and are measured on one spectrometer here on the right. We also use a second spectrometer to monitor the X-ray emission from the backlighter, and we combine both of these measurements together to perform our absorption measurements. And the real key advancement that we did to improve this platform is we designed, tested, built, and deployed a new high-resolution X-ray spectrometer, which we call EFX, for these types of measurements on Omega 60. So here I'm showing a comparison of ambient iron Zanes spectra, where black is the new spectrometer that we built, and green is the old spectrometer that was previously used for these measurements. And what I'm really highlighting is in the improvement to the spectral resolution. So we're looking at this feature here, this B feature. This is a little kink in the absorption spectrum. Here's a synchrotron absorption spectrum. This is a very high resolution spectrum of the same material. And you can see this B feature also emphasized in the synchrotron spectrum. This feature here is sensitive to both structural transitions in iron, the BCC to HCP transition in iron, as well as solid liquid melting. And similarly, this white line here, this main peak in the absorption spectrum, is sensitive to solid liquid melting as well as bond distance. So this is really demonstrating that this new spectrometer can start making these Zanes measurements for the first time at this facility. Okay, so now that we have an idea of the platform and the spectrometer, I'm going to go briefly through some of the results that we were able to obtain on Fe2O3. So we measured Fe2O3 Zanes and XApp spectra compressed above 700 GPa. On the left here, I'm showing the Zanes spectrum. This is the absorption coefficient as a function of energy. This is the same as the title slide. And on the right here, I'm showing the XApp modulations as a function of wave number. So again, just recall the XApp modulations. We isolate those modulations. We call that chi, which is just the isolated modulations. We often plot it as a function of wave number, which just goes as the square root of the energy. That's more by convention. And there's 2 features that I really want to highlight with this. The Preedge feature right here, this is due to iron-oxygen hybridization. So this feature is sensitive to how the iron and oxygen atoms interact at these extreme conditions. On the other hand, the XApp spectrum here is sensitive to the local structure. It's sensitive to the oxygen distribution around our absorbing iron atom. So first I'll talk about the XApp spectrum. The XApp spectra were analyzed assuming an ion distribution could be modeled as a skew normal. So again, recall the XApp modulations chi are given as this integral over our real distribution. And in our situation, iron is our absorbing atom, and this real distribution is the distribution of the oxygen atoms relative to that iron atom. And what we assumed is that this distribution could be modeled as a skew normal, which is a normal distribution multiplied by a skewing function. You can see those 2 different components here, as well as the red is the ion distribution. And what we find really interestingly is that the inference results show the distribution becomes significantly more skewed when it enters the gamma phase. So again, just to recall, Fe2O3, it was previously found that there's this theta phase between 150 and 400 GPa. And then there's this loss of diffraction lines. There's this loss of this long-range order above 400 GPa. And what we see here from our XAPS data is the ion distribution is very symmetric at 170 GPa. But then as we compress it up to this gamma phase, we see it becomes very asymmetric. And this is an indication that the oxygen ion potentials are becoming very asymmetric in this gamma phase. Now to talk about the Zanes results. This Preedge feature is from a 1s to 3D transition that is allowed through hybridization with the oxygen p orbitals. So sorry, that was a lot. But we're looking at a transition from a 1s state to a 3D state, and that's what produces this little peak before our absorption edge. A transition from a 1s to 3D state is nominally forbidden under the dipole transition just due to conservation of angular momentum. But the iron 3D states hybridize with the oxygen p states, and that's what allows this transition to become available. And we can see that transition, we can see that hybridization here, where I have the electron density of states as a function of energy. And we're looking at transitions from the 1s state into the iron 3D states. And we can see that there's a nice overlap in energy with the oxygen p states. Each spectrum was individually analyzed to isolate this Preedge feature. So here I have the normalized absorption coefficient again as a function of energy. Black is our data. We modeled these features as a Gaussian feature meant to represent the Preedge, plus a sigmoid function meant to represent the edge. We convolved this model with the spectrometer instrument response that we were able to characterize when we designed the spectrometer. And red is now the best fit to our data. And what we were able to do now is isolate this Preedge feature and study what's happening as a function of pressure. So on the right here, I'm showing the 1s to 3D, that's this Preedge features, full width half max, the width of that, and the area as a function of decreasing iron-oxygen bond distance. So we extracted the bond distance from the extended XApp fits, and we started a large bond distance and decrease as we go to the right. That's just an indication of increasing density. And the color of the plots is also corresponding to the pressure of each shot. So each of these points here corresponds to a different shot where we fired the laser. And what we think is happening here is that perturbations from the neighboring oxygen atoms cause the iron D states to broaden with increasing density. So the first order, nominally the 3D iron states are all degenerate. But when we put them in a cage of surrounding oxygen atoms, that causes the degeneracy to break because some configurations point towards the oxygen atom, some point away. This causes a change in energy. So for example, here this is the dz squared orbital, or the m equals 0 orbital, and here is the dx squared minus y squared orbital, or the m equals plus or minus 2 orbitals. And we can plot the energy difference between these two orbitals as a function of FeO bond distance, very similar to what we were showing earlier. And we see that this energy difference increases as we compress the system more, as the oxygen atoms perturb the iron states more. So to just verify this, we performed density functional theory calculations to compute the width of the unoccupied iron D states, and those are these red diamonds here. And those, again, agree that this state should be broadening as we increase density. So just as a last slide, what are the implications for this work? The Preedge feature is confirmation that iron and oxygen remain bonded above 400 GPa. So again, here's the phase diagram, and we had some uncertainty about what was happening in this gamma phase. And the XApps of the extended XApp spectrum show that the ion potentials become very asymmetric. And one thought could have been, is the system melted? What do we think is happening? But the Zanes show that the iron and oxygen still remain bonded at this system. So we think this could be an indication of some sort of correlated fluid where we have iron surrounded by cages of oxygen with no long-range order. So the analysis indicates that Fe2O3 maintains at least short-range order into this gamma phase. So with that, I'll put my summary slides up, and I just want to thank the NNSA, the SSGF, and Krell for supporting all of this work and making it all possible. So thank you. I'd be happy to take any questions.